Now I'm very happy to welcome our speaker, Paul Gow. So thanks very much, Paul, for joining us today. Just give Paul a quick introduction before we get started. So Paul has over 20 years experience working in the mineral exploration and development industry. He completed his PhD at Monash University, investing iron oxide copper gold deposits in the Stuart Shelf. Following several years in greenfields gold and copper exploration programs on the Gawler Craton in South Australia, Paul returned to a postdoctoral research position at CSIRO, investigating and modelling regional scale structural controls on mineralisation with a focus on porphyry copper deposits of Chile and New Guinea. He then held roles in copper-dominated mineral exploration and development, including District Geologist, Exploration Manager, and General Manager for projects in Australia, Brazil, and Papua New Guinea. His stewardship saw resource discovery and completion of project studies from scoping to feasibility level on IAGOD and porphyry copper mineral deposits. And he currently has his own copper exploration development company in Chile's coastal IAGOD belt. Paul joins us today from the Sustainable Minerals Institute at the University of Queensland in Australia, where he is Associate Professor. So Paul, thanks for joining us again. I'm looking forward to hearing more about this fantastic resource that you've been developing, the Northwest Queensland Mineral Deposit Atlas and the 3D compilation. So over to you, Paul, and we can get started.
Okay, thanks very much, Alannah and Macky and the Ore Deposits Hub team for having me today. It's a pleasure. And also thanks everybody who joined. I saw a lot of those names online, a lot of them familiar and a lot of them new. So thanks for coming along. Hopefully you'll hear something a little bit new about what we're doing if you haven't seen it before. Yeah, look, as Alannah mentioned, I guess it's a nice way to look at it as a resource that we're putting together to be used by the mineral exploration industry. We're looking at Northwest Queensland, which is an incredibly rich mineral province, and we're basically building an atlas of what a lot of those key deposits look like, and I guess looking at ways they've been found historically. Looking at how new technologies are being applied to them and what that might mean for future discovery. Look, before I go any further, I'm talking today, but I should note that Rick Valenta, Nathan Fox, and Mark Hinman, who are all here at the Bryan Mining and Geology Research Centre, have also done a lot of work on this project, and it was actually Rick Valenta in conjunction with the Geological Survey here in Queensland who essentially put the project together. Yeah, so look, where the project came from, this is a slide that some of you, I recognise your names there on the coming into the talk would have seen before, and it's something that Rick put together probably back around 2014, and what it shows is I guess the research and the new data that has been collected in Northwest Queensland and when that happened, and then that's up the top, and then down the bottom is the I guess the map of the deposits that have been found at least since about 1964. So there are a couple of things to note, I guess. Firstly, on the deposit discovery, you'll see that there was not a large increase in discovery depth, but it started going from surface that you hopefully can see up here where the mouse is, down to about 100 metres. So not going too deep, but there was that going undercover aspect as discoveries evolved with time. So that's one thing to note. The other point to note is that this shaded area in here from 1994 onwards is basically very thin on the ground in terms of discoveries. And that was part of the rationale for this project. So this project is funded by the Geological Survey here in Queensland as part of their new discoveries program, in that they are trying to add impetus and help out where they can to produce additional discoveries in northwestern Queensland. So that's essentially the rationale. So you'll see there was a lot of research happening, and it didn't particularly equate to discoveries. And I guess that's a timing thing, in that a lot of that research, if you'll see, started, it's flagged here as starting about 1994, which was on the back end of a lot of world-class discoveries. So I guess if you have a bunch of world-class discoveries, it's not a given that you're going to keep getting them. So it's partially time dependent as well, that lack of correlation. Look, to cover what we've done, we've included 28 deposits, of which I'll get onto in a minute, but five of them are really truly world-class deposits. They were discovered between 1882 to 2006, and you will see the metals and minerals that they cover, from copper and gold and lead and zinc, moly and rhenium, gold, uranium, and phosphate. So the northwest Queensland, the Mount Isa terrain, is one of those incredibly endowed terrains that you see around the world very rarely, where not only do you have world-class and large deposits, but you have such a variety of commodities as well. So it's a pretty special place that no doubt has more discoveries awaiting. Now, I guess what I should say, you'll see this is a magnetic image, a grayscale magnetic image on the right with a lot of those deposits marked on it. Not only the deposits that we've put in our atlas, but a lot of other significant deposits. And what you might see, and I guess we all know this from looking at magnetic data sets, as are so commonplace these days, is where you see a lot of texture is essentially where the outcrop is. So that you can see this type of texture around Mount Isa and out to the east. But where that image starts to get blurred is essentially where you're going undercover and your magnetic rocks are getting deeper and deeper. So that you can see here that as you head off to the northwest, the southwest, and off to the east as well, you're diving undercover. It's typically flat-lying cover all the way from the Cambrian through to the Cretaceous and younger. And also out to the east. So there's a deposit here, Eloise, that is probably under about 50 metres of flat-lying conductive overburden here. So just to give a feel that there is not only a lot of outcropping area in the Mount Isa inlier, but the inlier we know from the geophysical data extends pretty significantly under the thin veneer of cover nearby. So look, what we did, we wanted to get as much data as we can, and the deeper you dig, particularly in places like Australia, where the geological surveys and the national organisation Geoscience Australia are so active, there is a phenomenal amount of data and information out there if you take the time to look for it. And I guess we're trying to short circuit that search by mineral explorers in terms of putting as much of it as we can together, and particularly the relevant parts of it, because I guess, as we all know, society and science in general is becoming more and more data rich, but what is critical and it's the critical skills that we should be teaching all of our young geoscientists is what is actually the important information. Geologists are overwhelmed with information these days, so it's important to know what are the important bits. So we've searched from project owners, and I've been very surprised that so many mine operators and project owners, ranging from the larger companies to the smaller companies, are so generous with their data and information about their deposits. And I guess it sort of comes from the background that the search is becoming more and more difficult, as we saw from that previous slide. And I think people are starting to realise more and more that really there needs to be collaboration and sharing of data if we want to be successful and target those more difficult deposits. So this is just a quick overview of where we've been searching for data. And what we've put in our mineral deposit atlas, it's essentially twofold. So one, we have, I guess, what matches to you, if you remember when you were a kid, or we still have one at my place, is the atlases that you drag off the shelf. They're big, sort of A3 type sizes, and I know my kids absolutely love it to put it on the floor and flip over page to page and look through all the maps. So we've aimed for that type of approach. So, for example, we've gotten as many regional data sets as we can, ranging from the sort of thing you see here on the right. So this is the high map data, I think it is, from over the Tick Hill area. So it'll be one of the mineral maps. the geological maps, the geophysical maps, the ASTA satellite imagery, and geochemistry, and all those sort of data sets that we can get together and present them all at the same scale in a nice, clear way, so that you can flip from data set to data set and understand exactly what's what. So they're the regional data sets. So we've put them in, I guess, an atlas type, but it's a PDF. It's not hard copy, but it's a PDF that people can download. And the other part that we've put together is a 3D digital compilation. So we put those regional data sets in there as well, and I'll show you an example from the Walford Creek deposit shortly. So the regional data sets are one half of the picture, and the other part that is potentially more important and is very data rich is the deposit scale data sets. So I guess the objective has been to put the ore bodies into their geological context, and then there's been, I guess, a very firm focus on trying to map out the halo characteristics. So when I first started working on this project, Rick Valenta said to me, look, essentially one of the key goals is to think of yourself as an explorer. You're out in the paddock, you've drilled a hole, you have the core and you're looking at it, and you're scratching your head saying, are we near anything, or should we walk away? And if we don't walk away, do we have an idea how close we are and or which direction we should be moving? So that was sort of the objective, was to put that information out there that exploration geologists could use based on the standard data sets that exploration geologists use. The standard geochemistry, the geophysics, and the drilling, of course, and geological logging and recognition. So that's the deposit scale data sets. We wanted to map out the halo. But the other thing we wanted to do was put together a lot of data that is not typically used. And I've put this diagram in here. It shows the Osborne copper gold deposit. So you'll see the pit there, and a couple of sections from, I think it's probably Neil Adsed's thesis maybe. And then we have this, the yellow zones are the ore bodies that Chinova, who own the deposit, supplied to us. They supplied us all this data. And then I'm plotted here, for example, we've taken the oxygen isotope data that Neil Adshead collected for his PhD at James Cook University, and we've put it into the 3D model. Because you all know, and you've all seen, when you go and read a thesis, there's so much valuable information in there. But, particularly, for example, when this was done, I think in the 90s, we didn't have the great 3D visualization capabilities we have these days. So that it's presented as tables, as we have here on this slide, and some sections and plans, etc. But I guess we feel it's really valuable to put that into its 3D context, so you can start thinking about what it might mean. So there's the basic data, and then there's that more specialised data. For example, oxygen isotopes, high logger and hyperspectral data. And I'll show you some information from TEMA and some petrophysical work that CSIRO have done through the Eastern Mount Isa Inlier shortly. So the regional and the deposit scale data sets that we've tried to put together. Look, before continuing and looking in detail, I thought I would put up a list of the deposits that we've looked at. There are 28 of them, and we've documented them, I think, in about 22 chapters in our atlas, because some of them obviously cluster together. I've listed them here in terms of date of discovery. So you can see that the earliest discoveries were back in the 1880s, and then all the way through to about 2006 with the Rocklands copper cobalt deposit. And there have been a couple of things since then, most notably Minotaur Exploration has discovered the Jericho copper gold deposit, probably in about 2017. But these are the deposits that we've documented. So there are a couple of things to look at that immediately stand out when you actually put the deposits down and look at their information. And I guess the first thing, and we all know this, I guess, is if you look at the method of discovery, probably for those top 15, it is pretty much all prospecting, shaft sinking, geological mapping and drilling on the basis of that work. And that's logical. They were the technologies that were available in those days. And then you'll see at about probably the late 1960s, discovery methods started to change to soil geochemistry, stream sediment geochemistry, geophysical methods, etc., as those techniques became readily and affordably available. I apologise, no doubt there are people out there looking at this and thinking, no, that wasn't actually when it was discovered, or that wasn't the method of discovery, but it's actually a very, very subjective thing to do when you sit down and read all the literature about these deposits. So no doubt there'll be a variety of opinions. Let me see, the other thing to notice off this list of deposits is I've highlighted here in deep purple what I would call the truly world-class deposits. So for example, we have the Mount Isa copper and Mount Isa lead, zinc and silver deposit. You could probably put George Fisher or at least Hilton George Fisher in with that as well. And then you have Century, Cannington and Ernest Henry. And I found it illuminating when I sat down, put these in a list and sorted them by dates, because despite having worked in the Mount Isa Inlier for a long, long time, it's really interesting, and I hadn't quite appreciated what a rash of world-class discoveries there were in 2 years. So 1990 to 1991 was Century, Cannington and Ernest Henry all discovered in very rapid succession. And so when you look at it, they sit in the middle of a 9-year period from 1986 to 1995, when there was this rash of discoveries, and it was really the golden years in discovery in northwest Queensland. And that plot that we were looking at earlier with the research versus discovery, essentially that a lot of that research started from 1995 onwards. So it's basically on the back end of when these big discoveries were happening. The other thing that we had a bit of a look at was which of these deposits were actually discovered using what you'd loosely call conceptual targeting. And again, that's very subjective, as you say, what's conceptual targeting. It's also dependent on, I guess, what's documented and what's available to read these days. But you can see that those three key deposits, Century, Cannington and Ernest Henry, were all part of this large stage of conceptual targeting that happened in the 80s and 90s. So if you just to put some numbers on the discovery process, if you look at the discovery tools, so as I noted, in those early years, most of them were prospecting, geological mapping and drilling. That was 15 of those 28. 2 were soil geochemistry, 2 were stream sediment geochemistry, 1 was systematic rock chip geochemistry, 1 was air core geochemistry, which for those who are not familiar with air core drilling, it's essentially uses a rotating bit, but there's no water involved or diamond bit, so it essentially goes down through weathered rock and stops when it hits fresh basement. So it's essentially a method for sampling top of basement rock. That was the Cool Floor deposit, was that discovery. There were 2 with ground EM and 5 using aeromagnetic data. So 2 using ground EM. I guess if you did this exercise with some of the other terrains that have different mineral deposit styles, I suspect that ground EM, for example, may not be quite the discovery mechanism. For example, if you're in an orogenic gold dominated terrain, for example. And the 5 that were found with aeromagnetic data, it was really the and 2 of them were those large deposits, Cannington and Ernest Henry, and it was really a game changer. And people talk about new technology and step change in exploration. And for example, in Australia, people talk about RAB drilling being one of those step changes. But in the 80s, aeromagnetic data collection, or more importantly, data and image processing was a big step change that introduced a lot of discovery, certainly in the Mount Isa Inlier. Of having put this data together, I guess to learn a few things from the previous discoveries, I've put together a couple of examples from discoveries back from 1969 to 91, looking at some of these, I guess, more traditional techniques. So looking at soil geochemistry, the Century deposit was discovered in 1990, I think it was. And it was interesting. Until I looked at it in detail, I hadn't appreciated it was a soil geochemical discovery. And why it's really interesting is that often, and we're all guilty of this, we walk around saying, oh, everything's been explored, you're not going to find anything at the surface. And you know, for example, in Mount Isa, it's been heavily explored, etc. But the Century deposit was found using soil geochemistry in 1990, you know, well after there'd been a lot of heavy exploration. And what happened, it was a conceptual target. Those of you who aren't familiar with Century, it's basically a very, very fine-grained sediment hosted base metal deposit with some breccias and vein networks, as you can see in that area. But what happened was, it was CRA at that stage, who are now Rio Tinto, and they had a conceptual targeting program, and they thought they had the right sedimentary packages, etc., up there, I presume based on looking at the Mount Isa deposits. Reading some of the literature, it's interesting. They actually looked at the big Cambrian domes up there, which I think are the Cambrian limestones that have been domed by the Lawn Hill impact crater, which the deposit sits on the side of. And so they ran two 20-kilometre long soil lines across that dome. And as you can see here, where the deposit is, which is where this little black zone is, you get the kick in this case zinc and lead. So it was, you know, an interesting story in that people were attracted to these Cambrian domes. And basically, towards the end of one line, they went over the top of the Century deposit and picked it up in the soil geochemistry. And then there was the follow-up grid soils and etc. work that led to them drilling the deposit. So anyway, that's the story I've read and heard and spoken to people about. So there may be other stories out there. I'm always surprised that when you start talking about discoveries, how many different versions come out. So talking about geochemistry, the Tick Hill gold deposit was a rather it's a very interesting stream sediment discovery story. What happened in the, I think it was about the 1980s, you had guys like Bill Perkins working up at Mount Isa copper deposit, and I guess the consensus was coming around to it being an epigenetic structurally controlled deposit. And so Carpentaria Exploration, who were the exploration arm of Mount Isa Mines at that time, said, well, let's go and look for structurally controlled copper deposits in carbonate rocks in high strain zones, and looking for a broad analogy to Mount Isa. So they headed down south of Mount Isa and they did some stream sediment sampling, which you see on this plot. And what they did, you see the terrain here is relatively flat, and that was the Tick Hill pit in the middle there. So they did some RAB drilling out on the alluvial or colluvial covered areas, and they did their stream sediment sampling with bulk cyanide leach gold, and they pulled up a 6.95 parts per billion gold anomaly at the head of this creek, which they then you know, assiduously paying attention to detail, they followed up all the way up the creek and took these other samples, and eventually, following a lot of hard work, they used some systematic soil sampling to come onto Tick Hill and drilled it. So it's one of those stories. I guess that was probably in the mid 80s maybe. So there was you know, still surface mineralization being found in the mid 80s via geochemical methods. And then it doesn't look like a big deposit, 700,000 tonnes, but it produced over 500,000 ounces of gold. So it's you know, a great discovery. So looking at the geophysical data, which is really been dominant in the Mount Isa inlier, I guess, in the last 30 years. basically because everybody, well, not everybody, but a lot of people have been stepping off undercover and under the thin cover. So this is just to demonstrate, as we all know, I guess, iron oxide copper gold deposits, particularly those that are magnetite dominated, and even those that are hematite dominated, such as Olympic Dam, still have pretty significant magnetic anomalies. So this is the Ernest Henry deposit here, and you can see the mineralogy of the ore there. So you have the magnetite and chalcopyrite, carbonate, biotite, feldspar, etc., and quartz. And this is the Osborne deposit, which is another copper and gold deposit. You can see I've put a few photos of the ore in here. If you go, I'll just give a plug to our atlas while we're looking at this. Most of these diagrams are taken from our atlases. So, for example, we had Chinova, who owned the Osborne deposit, give us a lot of great photography of their drill core and hand specimens, and also donate a lot of data. So that, for example, what you see here, this is the Osborne deposit, which is a screaming magnetic anomaly, and this black outline is the ore lenses plunging off down to the southeast, and then curving, I guess, at depth. And while I was putting up the Osborne images, I thought, for interest's sake, for those who are interested, I've whacked the Falcon airborne gravity gradiometry image on here as well. And you can see that Osborne actually stands out as well as an airborne gravity anomaly. I guess what is a little less intuitive is if you start looking at the aeromagnetic data and lead zinc silver mineralization. And this is a diagram from the Cannington, Morone and Pegmont chapter that Rick Valenta put together. And you'll see that he's highlighted here. These are all lead zinc style targets or not targets, they're prospects where mineralization has been drilled. And you can actually see that, for example, Cannington itself has an aeromagnetic anomaly of about 1,000 nanoteslas. And then there's another one up to the north called Moronen that is much stronger. And it also does have a hint of copper and gold as well. So it's worth bearing in mind that out around Mount Isa and looking at this, the lead, zinc and silver deposits can also have an aeromagnetic signature. And I guess this sort of reminds me a little of if you start looking out at in the Warramunga province in the Northern Territory, where there's a lot of copper gold mineralisation similar to Tennant Creek. But there are a couple of targets out there where lead and zinc have also been intersected, and they've basically been targeted on magnetic anomalies as well. So it's not just an iron oxide copper gold thing, these aeromagnetic anomalies. Yeah, look, the last geophysical method I wanted to talk about was EM, electromagnetic data. So Walford Creek was an EM discovery, and again it was conceptual targeting by Western Mining. They thought they had the right, or my reading of the documents is they thought they had the right sedimentary setting out along the Fish River Fault, which is a strong, it's a large east-west trending fault, a growth fault with movement down to the south. So they went and ran some ground EM there and detected the pyrite lens that is associated with the cobalt copper mineralisation near the fault. And I just put this diagram up. This is another one from our atlas, and I'm actually going to show you this one live in a minute. So this is from airborne EM survey, and it beautifully maps the pyrite lens, at least where it's shallower than about 200 meters. Yeah. So that's a bit of a look through some of the traditional data sets, I guess, and how some of those large and small deposits were discovered. I thought also I would give you an example of some of the atypical exploration data sets we use that you know, they're obviously not recording discovery histories, but they're now being used for characterization of deposits for hopefully future discovery. And one of those, I guess it hasn't really been used for mineral exploration so much, but it's certainly at Mount Isa, it's been shown to be very useful, which is oxygen isotopes. So on the left here, this is all material from our atlases. You'll see the lead, zinc, and copper halos in RAB and diamond drilling from the Mount Isa Valley that hosts the large copper and the lead, zinc, silver systems. This is a 3D view of the copper ore body sitting against the footwall or the Paru fault. But what I wanted to show was the oxygen isotope depletion, which I guess has been well known, and this is based on work from Waring back in 1990. But you know, to my knowledge, it hasn't really been applied too much in mineral exploration. So that's one of these types of data sets that we're putting in the atlases that people can have a good look at and hopefully sort of understand what these large deposits look like in different data sets. Another one, and I guess this is becoming more, it's not so much a fringe technology anymore, it's becoming more and more common, particularly in resource drill outs, which is hyperspectral core logging. Now the Geological Survey of Queensland has done a wonderful program putting together representative drill holes from a lot of the large deposits. And as part of that program, not only are they collecting the drill holes and storing them in their drill core facilities, but they're also running them through a high logger that they have based here in Brisbane. So there's some absolutely wonderful data sets available, and that, you know, these things are freely available online, and we've included a lot of them in our mineral atlases as well that can be downloaded and viewed however you wish. There's some fantastic stuff coming out from Ernest Henry where I think there's probably on the order of about 10 holes have been put, 10 holes strategically placed to show the halos and alteration around the deposit have been logged with high logger. So this is really nice and shows us the mineralogy around some of these intersections at Cannington. So you can see this is the zinc and lead and silver peaks here. And in the shortwave infrared, which is great for mapping micas, you can see the yellow is white mica. So, for example, it disappears in the mafics and in the mineralized zone. The thermal infrared is much more useful for mapping quartz and feldspars. So you will see that the pink is silica, the orange is K feldspar, and the brown is plage. So So the thermal infrared is a fantastic data set that comes out of the high logger, and also TerraCore, which is another scanning technology. And you know, quartz and the feldspars are so important, particularly in the IOCG story in northwestern Queensland. And I just had two more data sets that I wanted to have a bit of a look through that people may not be overly aware of. Back in the mid-2010s, CSIRO, which is the Australian National Science Organisation, undertook a program where they went to a lot of the iron oxide copper gold or copper deposits in the eastern Mount Isa inlier, and they took a lot of samples down the drill holes, and they subjected these samples to a whole bunch of different tests, ranging from the TEMA that we're having a look at here, which is, I think, the TESCAN integrated mineral analyzer, which is essentially an SEM-based technology. So that they've mapped this mineralogy on these pieces of core, which represent about two centimeters diameter, I think. And so CSIRO did that, and they've published all this information. It's all available. So what we did as part of our search was to dig out that information, and we put it into our 3D compilation and models down the drill holes with all the high logger line scan data, which is essentially high resolution core photos. So we've tried to put all of this stuff together so that people can load this up, have a look at it, and understand what the mineralogy is, how the mineralogy is varying, both through the deposit and laterally away from the deposit, for example, using all of these data sets. So it's it's a fascinating resource. Now look, the last thing I wanted to touch on is something that I really wasn't aware of, and I'm sure there are a lot of people out there that aren't, is anisotropic magnetic susceptibility, AMS. And as part of this program, where the team of mineralogy data was being done, the same samples were used to measure the petrophysics. And the way it works is that we all know that rocks have a magnetic susceptibility, but what I really wasn't so aware of is that is anisotropic, and you can actually go and measure the orientation or the preferred orientations, the weakest versus the strongest of that magnetic susceptibility. And from that, you can then take a stab at potentially what the strain conditions were that reoriented the crystal, the magnetization within those various crystals. So CSIRO basically went through a lot of the Eastern Succession, and they've plotted them all on stereo plots here from the various deposits, where essentially K1, K2, and K3, which are the weakest to strongest magnetic susceptibility directions. And what's interesting is that sorry, I'm just trying to. There we go. So what we've done is put as much of this data as we can into our 3D models. So, for example, what you're seeing here, this is the Ernest Henry ore body, and some drill holes that CSIRO have analysed, and so they've actually plotted we've actually plotted their data, the direction of the magnetic susceptibility, which you see varies laterally from below through and above the deposit. Vertically, and also it's somewhat variable laterally as well, which I think we're still unclear about how that whole story will unravel, but it certainly makes for some interesting data to have a look at. Look, before I crank up one of our 3D models, I've touched on this. We deliver all this material online. This is our website here. I'll put the link up later. We also have it on this slide. If you just search for these types of words in any search engine, you'll hopefully come to this page. So that these Atlas documents can be downloaded, and then we also have what we call our 3D Atlas, which is essentially the 3D model and data sets that we've used to put all the information together. We put it together in a software platform called Geoscience Analyst, which is built by the Myra people who are associated with GoCAD. It's a free, basically, viewer that can be downloaded. But we also provide all the data in case anybody wants to look at it in any other platform, etc. So that's how it's being delivered. I think that's it for the presentation. But I just thought I would crank up one of our 3D models so you can get a feel for the sort of stuff that we're putting together. I note from the names that a lot of you may have seen this, some not. Essentially, what we've done is try and put all of the information into a 3D environment. So we start in at the regional scale. So, for example, with the satellite imagery, and you can probably see a few drill holes here from this is the Walford Creek deposit, and then we will put the geology together with that. So that you have a feel for the 2D geological mapping and its setting, and then we will drag out the 3D geology that we have that's come out of the various studies that have happened over the years. So, for example, here you can see these are the faults in blue, and this is the Fish Creek fault that I've selected here, and it's essentially a growth fault. And you'll see that the various stratigraphic units. This 3D geology was put together in 2010 under one of the GSQ funded projects. So we put together that's the geology, and then we'll also put together the regional geophysics where we can. So, for example, we have the radiometric imagery. And the magnetic imagery, etc., and any other data sets that we can find. For example, the airborne EM. So this is a grid of the Tempest airborne EM survey that was flown, and I think we've also put together some conductivity surfaces there, so that if you have a look at the, we'll put the 3D geology on with that. So you can see that this is the Fish Creek Fault, and this is the conductivity anomalies that that represent the massive to semi-massive pyrite layers. So all that sort of regional data we've tried to put together. The seismic sections that you will see there that were collected over there by Aon Metals, who own the project, and they've very generously donated all of their data to us. And then we will put together the deposit geology. So, for example, we have the cross sections through the deposit, and actually this is quite good. I've left on the conductivity surface, and you will see if we zoom in there that the mineralisation at Walford Creek. This is the Fish Creek Fault. The mineralisation sits in what they call their pyrite 1 and pyrite 3 units. And you can see that this pyrite 1 unit, because it's the shallower one, really dominates the airborne electromagnetic response. So that is really nicely being mapped, that pyrite unit, by the geophysical data. And lastly, I guess all of the models vary on what we have in them, depending on what data is available. So, for example, this is I'll just put those cross sections back on. Walford Creek, the owners, Aon Metals, have given us some of their representative drill holes, so that we've imported that drilling data. You can see it on the section here. And not only do we have the grade, etc., but we also have those high resolution core photography in there as well, so that you can have a really nice look at those different units that are there. Yeah, look, so it's hours of fun. This is one of the deposits, Walford Creek, and as I noted, we have 22 different chapters with 28 deposits in it. So we have a lot of this fantastic data online and available to download whenever you want it at our website. So look, that's a good look at. We're just wrapping this up now. I think later, for those of you in Australia or Northern Australia or in Queensland who will be able to get there, in Mount Isa, late November, we're having a face-to-face session where we're going to run through a lot of this information and data. So hopefully we may see some of you there. Numbers are limited. So you need to register quickly through the geological survey. Yeah, okay. Look, thanks, Alannah. That's my overview.
Thanks so much, Paul. If you could leave your last slide up there, that'd be great, just so we have something on screen. Thanks. Yeah. So fantastic talk. Really enjoyed hearing about this this resource. As we said at the beginning, is fantastic to have that, and it seems like something that would be good to have in more areas as well. So hopefully more groups can start working on something like that.
Yeah. Well, funny you say that, Alannah. Well, the Northern Territory Geological Survey here in Northern Australia, we have done a similar exercise for their rover field, and we're in the middle of doing that for their Tennant Creek copper gold field as well. And we're also working on northeastern Queensland, the tin tungsten systems up there.
Oh, fantastic.
Sorry to interrupt you.
Great. No, that's fine. Yeah, so I know you don't have so much time today, Paul, so we'll just get in maybe a couple of quick questions there. There's already a couple in the chat. So we've already got one there from Henry. So have you had any radiometric airborne survey over Ernest Henry?
There has been a radiometric airborne survey over Ernest Henry. But the issue is that it was originally covered by about 30 to 50 metres of flat-lying cover. So the radiometric signature from Ernest Henry was basically blanketed by that. But if it was exposed, you would certainly, and we see this from the data, you would certainly see a potassium and a uranium anomaly. And I'm sure you would probably see a thorium anomaly as well.
Okay, great. Thanks, Paul. We've got another one here from Dennis Achuki. If you'd like to unmute yourself, Dennis, you're welcome to ask a question.
Hello.
Hi, Dennis. We can hear you.
Good. So my question is, you spoke about TIMA data, which you said is basically SEM. So I wanted to know how do you translate that to be representative of a large scale area? Let's say you have a few drill holes and then you have TIMA data, and then how do you convince someone that we have a deposit here using that?
Yeah, look, I mean, as it sits, the obviously it's the perennial problem with drilling. So TIMA has the same issue. When you look at an ore deposit and you've drilled some holes into it, it is a very small sample that you're taking to represent a large system. So what you need to do is actually find some spatial variation and systematically sample, so that you can then say, well, this is what our mineralogy is here. This is what our mineralogy is further away. And I guess what we're hoping to do, and I haven't shown you a lot of information that has been put together about the mineralogical halos of deposits. I guess we've focused more on the technologies, but the very simple mineralogical halos that are delineated around the deposits in Northwest Queensland and that are presented in our atlases should hopefully give people a guide, so that when they have a drill hole, it's just come out of the ground and they're looking at the mineralogy and the alteration, they can say, well, this could be a type X or a type Y system. And then hopefully when they get their next hole, they can look at it and go, well, yes, it is a type X system, but for example, the mineralogy is telling us that we're going in the wrong direction. We need to go back the other way and drill, for example. So that's what needs to happen, is you need to use the detailed mineralogy that you see in that TIMA data to understand where you sit in a broader system.
Okay. Thank you.
Thank you, Dennis.
So our next question is from Tom Belgrano. Of these many datasets, which combination tends to have the largest deposit footprint in Northwest Queensland?
Yes, yeah. Well, it's really interesting and perhaps intuitive and not surprising, is that the biggest footprints you see are from the biggest deposits. Okay, and I guess what we often forget when we're looking at mineral deposits is that the footprint or the halo can be anisotropic. Okay, and it's typically elongated either along a structure or along your stratigraphy. Okay, that depends on how you're putting your fluids through. So that, for example, we had a look at some of those diagrams from Mount Isa, and you may not have appreciated the scale, but it's phenomenal. If you go to the Isa Valley, those simple elemental anomalies and the oxygen isotope depletion anomalies go for kilometres and kilometres and kilometres. And where you tend to find those anomalies is along strike. And in that case, a lot of your faults are parallel to the strike of your main units as well. So that the alteration and the geochemical halos, at least for Mount Isa, and I'd hazard a guess, or I suspect that Ernest Henry, for example, is the same, tend to be along your structural or stratigraphic strike direction.
Really interesting. Thanks, Paul. We've got two more questions here. Just quickly, of the kind of accessibility of this in the geoscience analyst, is that we can download that directly, or it's open source, or?
Yes, look, the way it works is the software that we've compiled it in is called Geoscience Analyst, and it can be downloaded. I should have put a link here by a company called MIRA, M-I-R-A. So if you search for Geoscience Analyst MIRA, you will get to their website, and it's a free download, so that you can then download that, and then you can download they're compiled projects that you can just download and open straight away in that software. And what I should add is as well as the Geoscience Analyst projects that we put on our web, if you download that zip file, it also has all of this, all of the data that we've imported just in its native formats, for example, just CSV files of geochemical data, or drill collar and survey files, or DXF files of surfaces, etc. So you can suck that into whatever you want to use to display and interrogate.
Great. And just to follow up there, was it all like initially loaded into Geoscience Analyst, or was there some built in? Just a question on GeoCAD. Sorry, I'm not. Yeah.
Maybe GeoH5 is maybe what you're talking, which is the file format. So what we did was take all the raw data and simply import it into Geoscience Analyst and format it nicely and everything. And then it just saves as one project that you can download and open up straight away.
Okay, fantastic. So there is a couple more questions, but I think we can also, maybe those people can follow up with you, Paul, on your email, if that's okay.
Yeah, sure. I think you can probably see my my email there, p.gow.
Yeah, we've got it. So
yeah.
That's great. So if anyone does have some further follow-up questions, do feel free to email Paul. And with that, thanks so much, Paul. It's really great to have you, and looking forward to exploring some of those compilations that you've made. So thanks very much.
Yeah, good. Look, thanks, Alannah. Thanks, Macky. It was great to be here, and thanks for everybody who was listening today.